Thank you. Well, he just made like one mistake. I'm not a senior engineer at Suzy Labs anymore. I was like until Wednesday. But yeah, I mean, I'm gonna talk about user space live patching. I'm João, so I've been at Suzy for like 2.5 years. And while I was there, I was basically bootstrapping the user space live patching idea inside Suzy. So we were basically developing a set of tools from the scratch. So we would be able to provide this feature of like enabling that user space applications could be live patched. So just like I said, I'm like formerly at Suzy Labs. If you need to reach me, make sure you use this mail, because I mean in the source code, if you download the repo or something, there's going to be the Moreira at suzy.de, and that mail no longer exists. So if you want to reach me, make sure you use my personal mail, okay? Okay. So basically, when we talk about live patch, what we're talking about is that idea, that eternal idea that software will have bugs. So whenever you are like writing software, if you are like a software developer, you know, I mean, there's going to be bugs. And because of that, you have like some serious problems like security issues. So sometimes the bug might allow users to do arbitrary things that you don't want them to do, or that thing may harm the performance of your system and make it like very slow or something like that. Or it may even lead to undefined behavior that will like break your system entirely, make your software crash or something like that, and you don't want that, of course. And whenever you need to fix a bug, what you do is that, okay, that software is running, but that thing is bugged. What you would do, I mean, you basically kill the process, replace the binary, restart the process. Normally, the loading time of the process, I mean, it will take like a few seconds, but some processes will take like much longer than that. For example, if you need to load the database into memory or something like that. And then the service is reestablished. And the problem, I mean, with this approach is that you have like a very long downtime, right? So in between, you kill the process and the process is like fully ready to run again. There's going to be some time where your system, I mean, your service is unavailable. And because of that, I mean, there's going to be some problems. For example, some services may take like very long to restart, as I just said. Some processes will need to load a full database into the memory, and if you need that, it's going to take like a few seconds or maybe minutes or even hours until you can like provide your service again. If you're like a bank, if you're like a system that needs to be fully available, you don't want that to happen. Besides that, I mean, sometimes you have like a server that has like active connections, and if you restart the service, these connections will drop, and you don't want your users to be like dropped suddenly or something like that. And if you're like doing large computations, so you took like months computing something, and we're close to the end, but now you have this bug and you need to fix it. So we will lose like the state of your program. You don't want that, right? So basically, that's why you want to use something like live patching. So in the kernel, we kind of have that, so it's already a thing in the Linux kernel. So if you take a look at the source codes of like the latest Linux versions, you will see that there's like a native support to live patching. So basically, you can replace kernel functions without having to reboot the kernel. It's like very cool. It's being used and being distributed by many companies. So I know that SUSE has a service like this. Red Hat has something. Canonical has something. Oracle has something. So everybody's like shipping solutions like this for their customers. So it's like a very successful feature. And in fact, it's like one of the products which grew the most inside SUSE for the last years. So it's like something very very special because it's bringing a lot of people to Linux. And we have this approach that we call Libpulp, which enables user space live patching. So Libpulp is not exactly a library. I mean, it has a library inside of it, but it's actually a full framework. So we have like a lot of tools which enable you to do the live patching. But besides that, there's also the library itself. So let me explain how this works. Before we proceed, talking about the technical side of Libpulp, I would like to talk about this concept of key essence. So this term comes from academia, and developers don't really use that. But as I also come from academia, I like to use that. So key essence means that this change that you are doing in the software, they should not like lead to an inconsistent state. So for that, you need to to apply the patches atomically. And a function could not be patched while running. So this is like a very small generalization of the concept of key essence. But what does it really mean? So imagine, for example, that you have like a function which is running. So let's call it function foo. And foo calls bar. And eventually, bar is running, and you apply a live patch in foo. So you just changed foo, right? And now bar is back running, and then it finishes. Then it's going to return to foo. So depending on how you do this change of function foo, imagine that you just take the function foo out of the memory and put like a new version of it there. Then you have like bar returning to a newer version of foo. And that's exactly what you don't want to do, because you're going to mess with the program semantics, right? So you executed half of the old foo version, and then half of the new foo version. So basically you have a consistency problem there, and this could lead like to undefined behavior. That's definitely something that you don't want to do. There's also this other concept that like patches should be applied atomically. So imagine that you are patching foo and bar. You actually want to patch both of them at the same time. So you don't want to patch first foo and then bar, because then you would have like a situation where you're like running a newer version of foo but an older version of bar. But it may be possible that, for example, foo calls bar in its new version, and it wants it to be in its new version. But since it's like not updated yet, there might be a semantic problem there too. So basically, imagine that this is like a very important rule. If you want to live patch, you have to apply the patch atomically, and these functions that you want to patch, they should not be running. And by not running, I mean they are not like currently executing nor into the stack to be returned to at some point in the future. So for ensuring this thing in the kernel, there are like basically two main models. These two models were merged into a single model in the kernel upstream right now. But in the beginning, there were these two ideas. So the first idea is that there's a boundary between kernel space and user space. So you have like a software running, and all of a sudden it will run like a syscall or something. So whenever it's like leaving user space to enter into the kernel space, you can basically track that there's some sort of like different context there. So if you want to ensure that no function is running inside the kernel, what you could do is, for example, whenever a thread is entering the kernel space, you just hold it, you don't let it enter. And then you wait for all threads to leave the kernel, so they go back into user space. And at this point, you know that no thread is inside the kernel, and because of that, obviously, no kernel function is running. So basically, you can just patch all of them, right? You just need to make sure to do that like atomically, so it's safe to patch. A different approach, which is a bit harder to implement, but it's kind of more fine-grained, is the stack unwinding approach. So basically, what you do is that you stop the kernel, you take a look at the kernel thread stacks, and you just figure out which are the functions that are running. And if the functions that you want to patch are not in the stack of any of the threads, then basically you can just patch them. Problem is, this works quite fine for the kernel, but how do you do something like that in user space, right? So basically, you are running user space program. There's no this thing between boundaries. I mean, what do you mean? I mean, user space goes into the kernel and then leaves the kernel. But a thread is never really only in the kernel side, right? So it's always like user space call in the kernel space, and not like kernel space call in user space. It doesn't make sense to. You will always be in the user space when you are talking about user space applications. And besides that, I mean, the stack unwinding approach could work. Yes, that's true. But the problem is that you have like many libraries which are doing like crazy stuff, and you don't want to have something like stack unwinding. Mostly because it's too complicated, it leads to too many false positives, and even in the kernel, it was like a bit hard to adopt this scheme in the beginning because of assembly code or because of things like long jump and set jumps. So it's a bit complicated here. So we had to come up with a new approach, which is basically implementing key essence in a whole new perspective inside Libpulp. And what we do is that we basically use the shard library models that user space and Linux uses. So and then instead of like having a boundary between user space and kernel space, what we do is that we have a boundary between your main object and all the shared objects that it's using. So basically, if you want to patch a library, you just need to figure out if the control flow of that program entered that library or not. So if it's not inside the library, then you know that you can just patch any function inside the shared object there. So basically, all you have to do is that we have to check if the library was entered or not. Okay, of course, it's not quite simple to do that. I mean, you just don't look at the process and have that in your hands. There's a lot of work to safely know if the library was entered or not, and that's how that's what I'm going to explain next. First thing, I mean, this project has like many different tools, as I said. So for now, let's just imagine that we can magically change functions. I'm not going to explain how we're changing functions right now. I'm just going to explain how we know if we can patch a function or not at this moment. And then, in the end of the talk, we're going to go into how we actually patch these things. So basically, just imagine that we clap our hands, and with that, we have like the power of changing the function inside the process, okay? So that's our cycle. Okay, I'm going to now talk about the Libpulp consistency model then. So who here speaks fluent assembly? I mean, who can write assembly code? Okay, that guy. Come on, please, raise your hands, because, okay, okay, we have some people, nice. Because, I mean, I'm going to get like really deep into the ELF files now and explain a little bit how these things are connected. And if you have a doubt, don't worry, just raise your hand. I will explain it as many times as we need. So if you have like some trouble with the assembly or with the ELF thing, just let me know. I mean, I make sure that I stop and explain that again, because if you lose a piece here, it might be harder for you to get the whole idea, okay? So basically, what we want to do is that, I mean, the ELF files, if you have like a library, it's a shared object, and the shared object is an ELF file. So ELF is like a format for the file. And the ELF files, they have like this dynamic symbol table, or dim-sim, which will basically hold the symbols, the reference to the symbols, to all the functions which are exported inside the library. So basically, imagine that you're talking about glibc. glibc has a printf function. So printf is a symbol. It's in the dynamic symbol table, and in the dynamic symbol table, you have the symbol and you have the address of that function inside the ELF object. So basically, whenever you load this library into a process, and your process, like your main application, is trying to call printf, what it's going to do is that it's basically going to look into the dynamic symbol table, figure out which is the address of that library, and from there it will know which is the address that the call instruction needs to go through to execute the printf function. So basically, that's how everything works. And the functions which are in the dynamic symbol table are the functions which are exported. So basically, if you are going inside glibc, you should be going through a function which is exported. So basically, it's just like an API, right? So if you're going inside glibc, you're going there through printf, scanf, fprintf, or some of these functions, and all of these functions are inside the dynamic symbol table. So this is like an important concept. And from that, we are going to derive a key essence model, so a consistency model. So first thing we use a modified linker to compile our shared object. And this linker, it's emitting the ELF, the shared object, for our library. But it will also emit like a new section that we call .elp section with an entry for each of the exported functions. So imagine that when the linker is emitting the shared object, it's emitting like a dynamic symbol table with one entry for each exported function. So we're basically doing the same thing with the ULP section. We have like one symbol for each entry in the dynamic symbol table. And we then modify the dynamic symbol table and make it point to the ULP entry and not to the function itself anymore. So basically, whenever the linker is trying to resolve the address for fprintf or printf, instead of like getting the address of the function itself, it's going to get the address of the ULP entry, right? So basically, we're like cheating the linker here. So this .ulp entry, what it will do is that it will save a reference to the function. So as each function has like a single entry, each entry is able to keep a reference to that function itself. So instead of like having the address in the dynamic symbol table, the actual address of the function, now you have this address in the ULP entry. And what you do is that basically, whenever the your code starts executing through the ULP entry, what it will do, it will just like get the address of that function, push it into the stack, and then jump into a totally different function called ULP entry. And this ULP entry function, it will just like say, okay, the library was entered. It will like keep a flag for that. And then it will just like realign the stack so as to make it exactly as it was when the function was called. And then it will actually call the function, and it can call the function because the address of the function was pushed into the stack by the ULP entry, okay? The function will execute, and eventually it will return to the ULP entry function. Then it will just like flag the exit, say, okay, the function is being left, it's not entered anymore. It will just like restore the return address and fix the stack again, and then it will return as it's supposed to. So basically, here's a schematic of how this should work. So you have like your main application calling fprintf from the libc. It will go through the section .ulp. We just like load the address of fprintf into R11. Of course, this is not precise assembly. It's just like a pseudo assembly or something. We put this address into the stack, and then we jump to this generic ULP entry function, which we will execute here. And here we are going to flag the entrance. We have this thing called sync the universe, which is something we will understand in a few. Forget this by now. Then we save the original return address. We fix the stack because since we are doing like calls here, the stack gets a little bit messed. We have to fix that. And then we call the address in R11, which is the address of fprintf. Fprintf executes there, returns. Then we reload everything and unflags that the library was entered, and then we just return to the address there. So basically, we're just like doing like a detour thing here. So it's just like I said before, cheating the linker to make sure that the process goes through our functions before it actually executes fprintf. Okay, so I said something about syncing universes, which sounds a little bit sci-fi, but it's actually much cooler than that. So basically, we want to patch the threads, right? But imagine that you have like a process with like many threads, or with a thread that never leaves the library. Well, we don't want to wait for all the threads to leave the library so we can patch. So basically, what we do, I mean, it's like a big problem, right? So what we do is that in Libpulp, we keep multiple different. You were taking their attention. It's just because you look too good. So basically, each thread has like a different universe. So imagine that you are like patching them, but you are patching each thread at a time. So you're not like patching all of them at once. So basically, we call these different versions like universes, because universe is cool, right? So how do we do that? I mean, isn't it like, aren't you like changing the .text section of the process? How do you change that function just for a single thread? Let's see that. It's like really beautiful, in my opinion. So the first thing, we keep like one global universe counter. So this is basically the general universe for the whole process. And besides that, we also keep like a per thread universe counter. So basically, each thread has like a local thread variable, which just keeps the universe version of that specific thread. So basically, we're like migrating the entire process, and then through everything that is migrated from the entire process, we migrate each thread one by one, right? And only when we like synchronize the thread local universe, we actually apply the patch to that specific thread. So one thing which is important for understanding this concept is this thing. I mean, we also use a feature in GCC. This is actually a feature in GCC. I did not have to change GCC for doing that for me. So in GCC, you can just like emit the functions with padding knob areas before the function. So basically, I just emitted the function foo here with like 22 bytes of knobs before the function, and like a 2-byte knob right after the function. So basically, my library, since I'm like already using a special linker, it's not a problem for me to also use a GCC feature to emit the functions like this for me. And since I have the functions like this, and since I can like clap my hands and change it in whatever way I want, I can just change it to this. So basically, what I do is that I replaced the 2-byte knob here with jump -24 function, which basically will make it go into that the beginning of that padding area before the function, and here it will execute some code for me, which is basically pushing an index, which is an individual index for each function, and then it will jump into a function which is like a universe checker. This universe checker will basically say, okay, let me see which is the universe for this thread. Okay, so it's universe 0, then just return and execute the original function. Is it like universe 1? Just go into new foo. Is it like universe 2? Just go into the newer foo. Is it universe 3? Then go into the real new foo, or something like that. So basically, before actually going into the function, you basically execute this universe checking thing. And another concept, which is important here, it's not exactly in the slide, is that now you know that we're not like actually overriding the function itself. We're actually loading the replacements into a different area of the process memory. So whenever you have like new foo, you actually just loaded it somewhere else. When you have like newer foo, you just loaded it somewhere else. Because you need all the versions to be in memory, right? If you have a thread which is in universe 0, you need this piece of code to be executed and not that one. So you cannot like overwrite this. And as I said, Libpulp keeps also a list of patched functions. So Libpulp is like a library, right? I said that before. I'll go into detail in Libpulp, but imagine that apart from all the changes we did to the toolchain, we also did load like a library with the process. So what this library will do is it will keep like a list of all the patched functions. Each node of this list contains another list of function versions. So imagine that for each function which was patched, you have like one node in the list, and for each node you have like a list of versions for that specific function. So basically you can just like go through this list and find what's the replacement for what. And as I said, the universe checking routine, that thing which is called in the prologue of the function, will basically select which detour to take. So just like I said, I mean, this is like a picture showing this list. So basically, you have like the detour route. So for the function bar, you have like a new bar function which is in the list, and for the function foo, you have like a new foo. As you can see here, how many patches were applied? I mean, does anyone have a clue? Okay, so basically we applied 2 patches here because new foo was applied with universe 1, right? So it was like the first patch applied is actually replacing foo, and the second patch applied is actually universe 2, so it's like replacing the bar function. Okay. Perhaps it's getting a bit tricky, a bit messy, but it's going to make sense in a few. So talking about Libpulp now. As I said, I mean, it's a library. It can be LD preloaded. You don't have like to link your process to that, because all you need is that the capabilities of Libpulp are in memory. You don't actually need this thing to be linked to your process. So all you need to do, for example, is emitting your shared object with the special toolchain. So this is actually like really nice for distribution. So for example, imagine in SUSE wants to provide a service like this. It's nice because they can compile glibc with the special toolchain, and they don't need to care about the process. I mean, about the applications themselves. They just like distribute everybody, and if the function if the function that they want to patch is into a prepared library, all they need to make sure is that the Libpulp was actually loaded with the process. So it's like a interesting feature for them. It's easier to maintain. Libpulp will provide the self-modifying capabilities, so that thing we do when we clap our hands is actually provided by Libpulp. It also will keep the data structures like those lists I just showed, and it's actually activated through outside from ptrace. So we're actually using ptrace to activate Libpulp. And ptrace is the magic. So ptrace is our clapping of hands. So what we do is that we use ptrace to attach the process and activate Libpulp. So let's see how everything works together now. As I said, there's like too many different pieces in the same idea, but let's go for it. So imagine that you have this process P. It's running, and it did load Libpulp with itself when it was first executed. It's going to use specially compiled libraries, and we need to fix this function in function F in library L. But we can't kill P, right? So basically, we have process P. Process P uses library L, which was prepared for being live patched. And there's like a function F inside library L, which needs to be patched. So we have this ptrace tool called trigger or T, and it's going to attach to this process, right? So does anyone here is clueless? Is anyone here like clueless about how ptrace works? Okay, so ptrace is basically the feature, the capability that's used in debuggers. So have you already attached it to a process using GTB? So that's ptrace underneath it. So basically, you can use ptrace to connect to a process and read the process memory and actually manipulate it. You can actually change the process memory by using the ptrace syscall. Okay. So our trigger, it's going to stop P, it's going to parse the memory and save all the context. So basically we're just going to save all the registers, all the register values for all the threads. And we're going to parse its memory and figure out what are the symbols, so which libraries were loaded, which are the symbols inside each library and things like that. So basically it's going to do like a full reading of the process. Then it's going to take one of the threads and overwrite the registers of it and redirect this thread to this patch apply routine. So what was exactly that? So basically, when you're attaching in ptrace, you can actually change the value of a register. So you have like this instruction pointer inside each thread. So you just save everything, and now you can just like take one of these threads and modify the instruction pointer into this thread, so you can just make it go to whatever function you want it to. So you just make it go through this apply patch routine. And then you just make the same thing with all other threads, but you just put them into this infinite loop routine. And all these functions are inside Libpulp, right? So it's just like addresses inside Libpulp. And then you just like restart P, right? So when you were like doing the modifications, everything was stopped. The process was not like doing any useful work. And now you just restart P, so you make sure that one thread which was redirected to apply patch is going to execute, and the other threads which were modified, were moved to the infinite loop, they would just like stay looping and not doing any work, so not harming your process. At this point, the patch apply routine will execute. So it's basically going to modify the to be patched functions. It's going to modify those knobs that we had in the prologue of functions. It's going to load a shared object with the replacement functions. So remember when I said that you have the replacements somewhere else in the memory? So it's just going to use DLC and load everything into the memory. So you now have the replacements and addresses for them. Then it's going to update the data structures, so that those lists you had inside Libpulp, they're going to be updated. Then it's going to interrupt, so it's just going to run like an int instruction, and it will return the control to the process which is attached, so the ptrace thing, right? So just like a debugger. So it's similar to the thing when you set a breakpoint in GDB that you execute, and all of a sudden it returns the control to the debugger. So the same thing here. We just have like a specially placed int instruction that you return control flow to our trigger. At this point, the trigger will restore the original context. So just like I said, we saved all the values inside all registers. We're just going to make everything back in its place, and then we can just restart P, and it will go back again, executing just like it was before the process of patching. So let's just see how things will work. So the process P was patched, and it will like call the function F inside the library L. And the library L is actually being entered by the thread. So basically, the control flow will go through the ULP entry function because of all those crazy detours we did. The thread local universe, it's going to be updated now. So that's the magic, right? When we clapped our hands, we incremented the global counter, but we did not increment the thread local counter. So when it goes through the ULP entry, the thread local counter is synchronized to the global counter, the global universe counter. So now it's going to be updated, and since it's been entered, this library will be executed in the newer version, in the newer universe. So the thread local counter is updated, then F starts being executed, and the first instruction there is like that jump, which goes backwards, and it will make the function go into the universe checking routine. And then the universe checking routine will verify that the thread local counter was updated to a new value, and then it's going to execute the respective function which needs to be executed. So imagine now a different situation where the process is calling the function F in the library, but it's a thread that was already entered, so it's not like a library entrance. So imagine that you have like a function in glibc calling another function in glibc, and you applied the patch after the library was entered, right? So the control flow will go through the ULP entries similarly, but now it's going to verify that it's not a library entrance. So the flag is set. I mean, the library was already entered. So it's just going to bypass the universe synchronization thing, and it's going to still be in the older universe. And now f is going to be executed, and when f executes, it's going to run the universe checking routine. And the universe checking routine will identify that the universe is like an obsolete universe. Then it's going to run the previous version of the function. So basically, that's the trick of like keeping multiple universes in different threads. Speaking a little bit about the trigger, it's fully based on ptrace, as I said. It uses the original binary to map all the symbols. So basically, when you are like trying to patch, let's say you're trying to patch Apache or like a software which is running for a long time. So basically, you're just going to take the original binary and use that to get like offsets for each function, and from that, you're going to derive all the symbols inside the memory by summing the actual offsets with the load offset and all that. It's going to check if the libpulp is loaded into memory before applying the patches. So if you try to call trigger on like a random process which did not like LD preload libpulp, it's just going to say, okay, you did not load libpulp, so you cannot do that. And then it's going to hijack the control flow of the threads and invoke libpulp routines, just like I showed you before. So it's actually one of the tools in the libpulp framework. When you're talking about live patch, okay, so you want to apply live patch, what is a live patch? So it's basically two different components. First is a compiled shared object, which is a very regular shared object, nothing special here. So you just have a shared object which has the functions which are used to replace the older functions. And then you have like the other part, which is a metadata file, and this metadata file will bring everything that is needed by libpulp to know where the patches must be applied, who is replacing who, and things like that. And of course, also check some dependencies or target build IDs. So for example, if you're patching glibc, you want to make sure that you are patching the right glibc. So just for doing that, you just check the build ID to know if that is the glibc you want to patch. So there's also this packer tool into the framework. It just gets like a description file for the patches, and it generates everything for you automatically, right? So you just like put this description file, the C file there as parameters for the packer, and the packer will just generate the metadata, the patch for you. So then all you have to do is to call the trigger and tell the trigger that okay, here is the patch file. So we also have like support for stacked patches, just like I have seen. I mean, you can apply like multiple patches, so we have like multiple universes. So you can just like have it's kind of unlimited, right? Not really unlimited, but you can just like apply as many patches as you want. And as I said, I mean, whenever you were like running a function, if this function was patched, the version of that function which we picked is the one with the higher universe. So sometimes you're going to be like in universe 3, but that function was not patched in the third patch. It was just patched in the second one, so it's going to have like a replacement in universe 2. So we're just going to take the function of the 2, right? So we can also like support unpatching. So for unpatching, what you do, it's pretty much the same thing as patching, but it goes against the notion that you have to decrement the universe. You're not decrementing the universe. You're actually incrementing it again, and you're just marking the functions in that specific universe that you want to remove as deactivated. And whenever you are running, picking the replacement for that specific function, if that specific replacement was deactivated, you are only running it if that's exactly the same universe of the thread which you are into. So by doing that, you just prevent that that function is not executed if that thread was not migrated into the newer universe yet. So basically, this is more or less how the tour lists are in the end. So you just have like a function foo and bar. So you first applied one patch here, which has this universe 1 and new foo. Then you applied a second patch, which was a a replacement for the bar function, but also a replacement for the foo function there. So these two are in the universe too. And then you have like the third patch, which was another replacement for foo. But then you realize that that third patch was actually gibberish. So what you did is that you just unpatched it, and then you, instead of like actually taking it out of the list, what you did was just like saying, okay, it's inactive. So it's only going to be used if the thread is specifically on universe 3. For overheads, we actually compiled glibc with support for Libpulp, and we did run spec using this specially modified glibc. We verified like a 2% overhead. And then we implemented like a very, 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 very bad use case for this thing. So imagine that you have like the Fibonacci function. So it's actually calling itself recursively, right? So it's one function calling itself. And in each call, we were doing like very small computation, apart from like calling itself again. So we applied a patch to this function, which is being like recursively called. And then we made it run. And we verified that for this case, we had like a 50 times overhead, which is like a hard price. But if you imagine that this is like the very worst case scenario where each function which is being called is live patched, and each function which is being called is like doing basically no computation. But I mean, it's doing a little bit of computation, but it's doing like a lot of calls to functions which are also live patched, then you just can't understand why this is like so bad. But I mean, 50 times, sometimes you have to pay the price if you want to fix a very critical thing. I think we in SUSE we think it's like doable. Okay, it's not that bad. I mean, it's not something that forbids us from using this thing. I mean, the 2% overhead is like the real thing here, because it's the price you pay no matter if you are patching or not. So if anyone wants to take a look at the sources, this is the repository for everything. You have like a lot of tools there. If you just like to play around with processes, if you want to hack stuff, if you want to take a look at process memory, there are like a lot of examples there on how you can do that just by taking a look at the Libpulp sources. So it's also like interesting for you if you want to study these things. That's it. I mean, my time is almost over, but I think we can like have like 1 or 2 questions there.
Yes, please use the microphone.
Seems to be a good feature and has good motivations, but it seems also that for applications that handles security critical applications that handle sensitive data, for example, it seems to be a free ticket for an attacker to get access to your memory. So is that discussed in the community, or security is discussed in the community for this feature?
Yes, I mean, just like it's the same thing for user space, and it's the same thing for kernel space. I mean, a lot of like security people, they just like hate the live patching feature because they're just saying, okay, come on, I mean, it doesn't make sense. I mean, you're like opening a door and allowing people to go here. But I mean, if you think deeply about this is like the same problem about Linux kernel, loadable kernel modules in Linux, right? So you just allow code to be loaded into the kernel space. I mean, it doesn't make sense. So basically, you just should have like something which is monolithically static and that will not change. And by that, you just make sure that nobody is injecting code into your kernel space. Okay. But then you just say, okay, but I mean, the loadable kernel modules is like a very important feature. It's very nice. So all you have to do is to audit the code perfectly and make sure that loading modules is not something very complex. So what do we do? I mean, just audit the code and make sure that it's like running okay. And I think it's pretty much the same thing for live patching, right? So I mean, it's like an important feature for a lot of people. And how do you make this secure? I mean, just audit the code. Of course, nobody will ever say it's like 100% secure, because nothing is ever 100% secure. But I mean, it just gives you the capability of fixing things. And it's actually something interesting, because you can actually use live patching for fixing live patching features. So if you have a bug in the live patching capabilities, why not like use Libpulp to fix the bugs in Libpulp? You actually can do that, right? But yeah, I mean, I totally get what you're talking about. Like, okay, this might be used in a malicious way, but just like everything else. That's my opinion, of course.
So when you say that the patching thread is going to stop the process, you still have ways where the kernel is going to interrupt user space, invoke user space, for instance, signals. Do you need to handle that? Do you have any mechanism in the kernel to make it uninterruptible to delay signal delivery somehow? Or is that a limitation in user space? For instance, your library cannot register signals or something like that?
Yeah, I mean, you actually have to take care of the signals. So basically, it's actually a fun question because sometimes I was like implementing this thing, and I had this process, this trigger process connecting to the process which I was trying to patch, and something was going on, and I did not know what was going on. I mean, why is this thing not working? And what was happening is because I mean I was getting like a sig-term signal, a segfault signal, because there was a bug in the library, but I could not see it because the attached function was actually collecting the signals. So whenever you're sending a signal to a process which has like a debugger attached or something like that, that debugger will actually collect the signals. So all you have to do, if you are like receiving a signal in your process, you just have to handle them into your debugger, right? Into your attaching process. Doesn't make sense? You're making like an ugly face.
No.
Okay, but yeah, I mean, I mean, yeah, I mean that's the thing. I mean, when you interrupt the process from the external side, you connect with the ptrace thing there. This thing will work like a shield for all the signals which are coming. So basically, you just have to handle it there. I mean, it's not something that we handle currently because we did not have the time to implement that yet. I mean, as I said, it's not like a industry-ready product. This is just like results of 2.5 years of research, but that's the concern.
My ugly face is because after you finish patching, you need to re-deliver the signal somehow. For instance, it might not be a seg fault, but it might be a user one signal, and the program actually handles that. So is there any limitation on what the user space program that supports live patching can do, or can you just live patch any program, any user space program you want?
Okay, let me think about it. Yeah, I mean, you definitely need to deliver the signals. That's something that you do. I mean, you need to do. For sure, as I said, it's not something that we do currently. We did not care about these things yet. But this is something that you actually need to do. And in terms of signals, specifically talking about signals, there's no limitation I can think of. I think if you just handle everything correctly from the attaching process side, you can just like deliver the signals. Of course, that there are things which are like critical here. So, example, if you have like timeouts or something like that. So, I mean, you're stopping everybody, and if you have like a critical thread which needs to deliver like a message in like a very short time or something, it's going to be stopped, and that connection may drop. But that's something you already expected in non-real-time systems. So, for example, you need to answer this request like real quickly, but it was the OS took it out of the processor, then it's going to take longer. So it's something similar like that. But I don't see like a limitation in terms of signal, at least, no.
Okay.
Anyone else? Okay. Out of time?
Yeah. So there is no more time. Thank you. They say thank you to you all.
Thank you, guys.